Hi everyone. In this lecture, we are going to learn about Euler-Totient function or Euler-Totient theorem. Okay. So first, see these two equations. First one is uh, the modulus inverse of time. Okay, and we know already we already know the solution of this. And what is that? It is x is equal to a to the power p minus 2 modulo p. And GCD of a comma p should equal to 1. And this is the statement of Fermat Little theorem. Now, what if your modulus is not a prime number and it can be a composite number as well? So, how you can calculate the modulus inverse using composite modulo? So, using Euler-Totient theorem and Euler-Totient function, we will calculate and find the value of x. Okay, and here the there is the same condition for the co-prime between a and m. So GCD of a and m should be also 1. We have used this the first equation or Fermat Little theorem several times in the competitive programming questions, and we already know a beautiful modulus value which is 10 to the power 9 plus 7, and which is also a prime number. So we have there you may miss this condition and you may have ignored this condition and you have directly applied this equation and get the modulus inverse of a modulo p. So why? And most of the time you uh, like solution get accepted. So why? Because your a value is always less than m, because you have also applied modulus operation on a as well. Okay, so your a value is always less than m there. Like after some calculation, your a value is less than m. Okay, so there doesn't have any chance between a and m should become should have GCD greater than 1 because m is prime number and the only factor of m is 2m, 3m and other number, and which is greater than going to be greater than a. So they that's why your solution got accepted. But here you have to take care of this condition. You can't ignore this condition here because m is uh, not a composite number, and there is a chance that even if a number is less than m, but their GCD between a and m is not equal to 1. Okay, so you have to take care of this condition for applying Euler-Totient theorem. Okay, now let's discuss the Euler-Totient function first. What is that? So it is just a n. We represent the Euler-Totient function in this way. You can call this phi, and let's first write the value of n in form of composite number. So which is p1 power e1, p2 power e2, p3 to the power e3. Okay, up to pk to the power ek. And what is that? P1, P2, P3, P4 is prime factorization of n, and E1, E2, Ek is their power. Okay. So what is the value of phi n? So it is nothing. It is n multiplied by, you know already this notation. This is for the series multiplication. And you have to write 1 minus 1 divided by P of I, P of k. Okay. You know already k is from 1 to k, all the prime factorization of n. Okay, this is the value of phi n. Okay. Let's calculate the phi n value for a prime number. Okay. Prime p. So what is value should be p multiply by 1 minus 1 divided by p. Okay. And the p has only one prime factor, which is p itself, and that's why I have written only one this bracket. So you got 1 p minus 1 divided by p, and finally value final value is p minus 1. So for prime number, your Euler tangent function always give you prime minus 1. Okay, so that is one result. Let's move to our Euler tangent theorem. So Euler tangent theorem states that a number a and a m, which is any composite number, and if they are GCD, or if GCD, like both number are co-prime with each other, then then a to the power phi of m is equal to 1 modulo m. Okay, so this this is the statement given by Euler-Tangent theorem. Okay, and how you can use this? Let me change the color. Okay, how you can use this expression to get the solution of this equation. Okay, so let me write this equation in the more general form. Okay, so it is going to be a multiplied by a to the power phi of m minus 1 is equal to 1 modulo m. Okay, this equation is same as this above equation. I just uh, splitted it. Okay, so now can we add a multiplied by x is equal to 1 modulo inverse of m. Okay, now where x is equal to a to the power phi of m minus 1. Okay, and what is this x? X is nothing, just a modulo inverse of a modulo m. Okay, and that is your answer. In most general time, you can write x is equal to uh, let me, okay, let me write this expression clearly. Okay, so you can write above equation a inverse is equal to a inverse modulo m is equal to a to the power phi of m minus 1. Okay, uh, x is equal to a to the power phi of m minus 1 modulo m. That is your final answer for Euler Tangent theorem. Okay, so we already got the value of x for this equation. Okay, now can we prove Fermat little theorem using this result? Yes, we can prove it. But how? So we already know that m is prime number. Okay, m is prime number for Fermat little theorem. Fermat little theorem. Okay, so x is equal to a of what is going to be the phi value of a prime number, we have already calculated here, it is p minus 1. So what we have to write here? M minus 1. Then again minus 1, because there is a second minus 1 here. Modulo m. Okay. And you can write a is equal to m minus 2 modulo m. And you can replace m with a p, because m is a prime number. Okay. So here you can see that we can prove the Fermat little theorem using Euler-Totient theorem. Okay. So this is all about how to find modulus inverse of using composite prime number. Okay. Thank you.